in the standard contact space. Okay, so so the main theorem of this paper relates to non-classical invariants. One we've talked about a lot this week, so the linearized Legendrian contact homology, and one we haven't that I'll define, the generating family homology. So I'm going to state the theorem and then define things, so I'll put it over here. So so there's going to be some term. Maybe I'll underline the terms that I'm going to get to. I don't know. So so F is going to be a linear at infinity generating family. Oh gosh, this wobbles. All right. Okay, so the main theorem says that if you have a linear at infinity generating family for L, then there exists a graded augmentation epsilon for the Chekhanov-Eliashberg DGA for L. Right. So if you have a linear infinity generating family for Legendrian knot, then there exists a graded augmentation for the GGA for the knot, so that the homologies are isomorphic. So another way to say that is that the set of generating family homologies so like this sort of like F over F for L is contained in the isomorphism types. Yeah, up to isomorphism. But. Okay, great. So yeah, so I'm going to define some things. Let's see, I put the working colors over here. So let's see. So yeah, so we're going to talk about, whatever this means, generating families. We're not going to talk about too much about augmentations because we've been talking about it. We'll talk about the homology. That's good. So the idea in this paper, see, I think I can fit it. I don't want to ruin the beautiful sunset, but I think there's space. So the idea is that, we're talking about sort of existence of generating families, F, right, for an L, and we want to relate it to augmentations. Epsilon for the DGA of L. And so how do we do that? Well, we go through a sort of combinatorial tool called normal rulings. And then it's sort of like a combinatorial tool on the front diagram of a Legendrian knot. They'll say for L, but it's really like a front diagram sort of thing. And these are all sort of like existence sort of statements. Yeah, and so I'm going to focus more on this side of the thing because this is sort of the talk for this side of the story, but I didn't know if someone would more talk about how to get back and forth for here, so I'm not going to say too much about this, but they use what they call a splash construction, which is similar to dips, if you've heard of it. And since I'm not really going to talk about it, I'll just say a few words where you sort of take the Lagrangian projection and you, it's a way to make the differential of the DGA easier at the cost of adding a lot more generators. So you sort of take a lot of strands of the Lagrangian and you either like pull them under and up or over and down, and it makes it like more complicated, but it makes it easier to compute, sort of. So that's all I'm going to say about that. And then on this side, you sort of have like a Morse complex. You have some sort of Morse complex, and you know, there's some like bifurcation analysis. Of a Morse complex. So that's just sort of an overview. I don't know, I didn't really make an outline, but it's sort of going to be like, I guess this will be 1. Well, I guess intro is 1, but this will be 1 and 2 and 3, and then I'll try to talk about some more recent techniques at the end. Okay, good? All right. All right, so let's talk about generating families. All right. So generating family is a family of functions that in some way generate your Legendrian. It's sort of, and you get a homology by basically, it's like a singular, relative shifted singular homology, or you can think of it as like a relative Morse homology shifted. But here's what a generating family is. So, right. Oh. So not all Legendrians have generating families, but if it does, then it's a way to have a function. Oh, and then so let's see, just to give some, here's where I need to make sure I use the right notation. So this Rn, I'm going to call the fiber, this is sort of, and I'm going to use x's, and so you have a family of functions over this R here, which is parameterized by a t coordinate. Right, so if this is a generating family for L, then you can express L in terms of this family and like the critical points of it. So yeah, here X is the Rn coordinate, so this is sort of a, you know, a fiber critical submanifold of 0 is a regular value. And right, so yeah, so what you want to think is that the fiber-wise, the critical values over this fiber critical submanifold sort of trace out your front diagram, and we'll see in an example in just a second. And so, right, so this is like a very non-compact set, so we want some sort of taming conditions at infinity. So that's where the linear at infinity comes into play. And all that means is that outside of a compact set, f is a linear function. So, yeah. Great. Okay, so let's do an example just to make sure we understand the definition. And we're gonna do the unknown. Okay. Oh, my pen's already getting lighter. All right. Tell me if people start to not be able to see. Right. So here's our t parameter. So for every t, we're gonna want a function. Here we can use the fiber dimension big N. We can just use it to be 1, which is why I chose it, because I can draw it on the board. So what we're looking for is right, we were looking for r cross r to r, but really we're thinking of we're finding functions ft just from r to r, whose critical points sort of trace out this front. So, right, okay, so, for t, before we see anything on the front, we want it linear at infinity, so we're going to have just, some nice linear function. So this is x here, this is, this is z and this is z, the same z. And then as we move forward in t, we approach this left cusp, and we're going to see right after we're going to see a burst of critical points at the cusp. So right after, we're going to see sort of still going to look linear until we see a sort of, tell me if you can't see this well enough, but the idea is that like these critical points here correspond to these 2 points here. Maybe they should be a little closer, but maybe this is really that. Right, and as we go across, these critical points sort of separate in value. So maybe here we're going to see some sort of this sort of thing where, here we go. They sort of come back together, and they sort of die at this right cusp together, and then here we're going to go back to our nice same linear function. Good? Yeah. Okay. Right. So here, let me put this in my notation. The front, I'm going to call the front diagram L. Front diagram. Again, I didn't pick this notation, so yeah. Right. So just to point this out, with this generating family, we can describe the front diagram by, is this still here? Yeah. In this way. So right, so we have t values and the critical values of ft give us our front diagram. So it's a very nice sort of thing to have. All right.
Deepa, is this really the notation they used? Or what
Yeah.
is this notation?
Yeah. I know, I was like, well, since I'm not giving a lot of details, I don't want to
Okay.
use different, yeah, it really bothered me, which is why I'm using my notes more, because I'll revert back to better notation. Sorry, that was a little rude. Yeah, okay. All right, so quickly, just some Right, this is not a unique sort of construction, right? So in particular, there's two sort of equivalences in generating families. So you can sort of precompose F with what we call like a fiber preserving diffeomorphism. So, think about maybe changing the slope and sort of, I don't know, I'm not clear, like making it fatter, some of these things, but we don't want to change the critical values at all. Right. And we can also increase the dimension of the fiber. So that's like what is the big N that I'm using. And we do that by summing with a non-degenerate quadratic in a new variable. So we have an f tx, and we're going to change it to a ft x is right. Yeah, I use x as the t. It's bad. Xx prime, which is just equal to f of tx plus some non-degenerate quadratic in the new variable. So this is, we call this a stabilization. Again, I don't know, some things in this field I feel like need to get a little more creative with the names. It's not at all like the zigzag stabilization, but in this case, I guess it's sort of okay to call it a stabilization because we also have the property that if, here I guess I'm using the front because I'm going to talk about a rotation number, but if your Legendre knot has, or the front has a generating family, then we have the rotation number is 0, and the Thurston-Benniken is maximal in the smooth knot type. Right. So this is why, like, if Legendre knot has the zigzag stabilization, it's not going to have a generating family. So I guess we can sort of get away with calling this a stabilization. But yeah. Okay.
So you restrict yourself on 2 dimensions.
In this talk, but you can have generating families for higher dimensional Legendrians. Yeah. Okay. Good. Any more questions? No? Okay, good. Okay. Right. Okay, great. So in practice, I don't. I guess maybe some people construct generating families, but the invariant is a homology associated to it. So let me explain how you get that.
Yeah, sorry, maybe I have a question.
Sure. Yeah.
If I give you a front,
Yeah.
can you tell me offhand if the corresponding Legendre has a generating family or not?
With a little bit more combinatorial data, and we'll sort of see that later in the talk.
Okay.
Yeah.
Can I also ask a question?
Sure, yeah.
In the higher dimensions, if you have
Yeah.
a stabilization, like the other kind of stabilization, the zigzag stabilization,
Yeah.
is this thing still true that there's no generating family? Like,
Yeah.
corresponding to
Yeah. Yeah. I don't really think about higher dimensional stabilizations, but yeah, you want basically the nicest Legendre in this.
In higher dimension, if you have a generating family, the Gauss map to Humour is trivial.
The rotation can be stabilized.
Okay, you also have the rotation.
You can stabilize in the same form.
Yes.
But, so those are two different statements, but they're both true.
Well, okay, but there is a proof that this zigzag is not a generating family. For roughly the same reason as it doesn't have a sheet, so you can boil it down to that.
No, but it's just, I mean, you trace the values of some more function, it's clear that there's a zigzag.
Yeah.
But it's on
That's
level
why
sheets.
that's separate.
It's on level sheets, and it's on level sheets with the slope.
Yeah, all of these concepts are related, but you can actually try to like construct one with a zigzag and you'll run into some issues, yeah. Well, it's one way, I guess, yeah. Right, okay, so from a generating family, you construct what's called a difference function. Right, yeah, I guess define the difference function. Let's see, what do they use? Yeah, x, y, t. Called a difference function because you're just taking a difference in a fiber. Right, and so this difference function has the properties that the positive valued critical points of W are in one-to-one correspondence with rave chords. Or, you know, if you'd rather, sort of crossings of your Lagrangian projection, and the values. The values are just the rave chord heights, lengths, I guess. Sorry. The lengths, or you know, like the crossing heights. I don't know. So this function sort of, the critical points of this function carry a lot of the information we're gonna want.
Maybe it makes sense to say that like for different functions, can you take two different generating families, and then you get like bilinearization?
Yeah, so, yeah, I'm sort of working with one
Right.
generating family for one Legendrian, but you could have, you know, if you have like a link, you could have different ones and
Oh, but even not, I think this idea is originally like due to Pushkar.
yeah,
To say like, okay, so you can have a difference function for one generating family, but you can also take two.
Yeah.
This way you can get the
definitely, yeah.
bilinearization.
Yeah, no, that's definitely true. Absolutely, yeah. Good, okay, so. Right, so the generating family homology is gonna sort of capture these critical points of W. So. So we have to sort of add a shift in to sort of take care of the fact that we can change the fiber. And I'm just we're working over Z2 today. And we just pick a delta, so, so that between 0 and delta, we don't see any critical points or values, sorry. So yeah, so I should say that this correspondence here. All right, so the positive value of critical points correspond to rave chords. So you sort of see symmetry in positive and negative values because you corresponds to going up a rave chord or down a rave chord. At the value 0, there's a more spot submanifold. That's just an S1. So we sort of want to go up from 0. And I think of this as a Morse homology of just the positive valued critical points. So obviously it's the same. Right, okay. And so right, so this set here is what's going to be the Legendre invariant. So that's what Trainer and collaborators did. Isomorphism types, right, generating families. Right, good. Okay, so that's sort of generating family homology in a nutshell. Any questions so far?
Sorry, generating families or generating family homology?
Both. Right.
But did you define isomorphism type? I mean, you defined some moves on generating families.
Yeah, I was gonna sort of, right, so, yeah, so basically what this, I can say a little bit more, what this invariant is, so you can look over all F, or you can look over like classes of F up to like the stabilization fiber preserving diffeo. But you still need to look at the whole set because a Legendrian can have multiple generating families with different isomorphism types. So it's again, if you feel more comfortable with augmentations, you can think about how, the invariant, you can like look at this set as an invariant. So, is that a good? Okay. Yeah. Okay, so so from our idea here to relate generating families to augmentations, we want to go through normal ruling. So I'm going to say a very little bit about this. The definition is very combinatorial, and you sort of need to get your hands on it. So I'm going to explain it sort of hand wavy and do an example. Hopefully that's okay. Right. So so ruling is a decomposition of a front diagram. I guess I put my notation that that's L, which I erased. Okay. Let me just write a little bit and I'll explain it. Okay, so we're going to take a front diagram. We're going to decompose it into paths that don't meet except at cusps and crossings, where you can have, let's see, so you have a cusp, or a crossing, and you can sort of color code the parts to have, I'm gonna drop stuff. Okay. Right, so these paths meet up at a cusp. Can just meet up at a crossing like that, but you can also have one sort of going here, and then instead of going through the crossing, going back up here. And this is what is called a switch. And you can actually determine the ruling just by a set of switches. So we'll see in an example.
So you have to switch colors at a cusp.
Yes, yeah. Yeah, you can't go through a cusp with a path. That would be good to say, yeah. Sets of switches. Okay. Right, so, right.
So in particular,
Yeah.
that is the only orientation you're allowed. Like, thinking of this actually as a front diagram, you can't actually switch this way. Like in the cusp direction.
Oh, you mean side to side?
Yeah.
No, yeah, no. Right, okay, so, right, let's just do, it'll be clear with an example, so, oh, right, and one more thing before this is that, here's where I'm gonna get very vague. Certain configurations of switches are called normal. I could draw it out, but I don't think it's particularly useful in a talk. But there's sort of a combinatorial description in here, but Caitlin Leverson has really nice pictures of what is a normal switch in one of her papers. So I would say if you want more details, I would go there. So this is gonna be big, but. And again, I'll point out in the example just to give an idea. Right, a certain configuration of a switch, not switches, but of a switch, make it normal, and then a ruling is normal if all of its switches are normal. Okay, great. Okay, yeah. R.
Sorry, what is the configuration of the switch?
It just has to do with like if, how these meet up. I'll show you an example. Yeah, yeah. Okay. Okay, great. So we got the trefoil. Right. So let's label the crossings S1, S2, S3. And so, right, so I claim that, we're about to do this. Yeah. That the rulings are going to be given by, S1, S2, S3. Is that gonna give me, can people see like here? The line isn't too low? Alright, well, yell at me if you can. Okay. S1, S2, let's see if I have space here. It's never good to hear from a speaker. Okay. Okay, so what does this look like? Right, and I claim that, I can claim anything since I didn't really give you the definition, but these three are normal. So this one is not normal.
What does your notation mean? It's like whether or not you.
I'm gonna draw. It's whether or not there's a switch at this crossing. So, right. So what this one's gonna, so S1, S2, S3 means we're gonna switch at each one. So we have, I'll get out of the way in a second. Right. So we switch, I think go here. So, right. So this is switch, 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 right? People see that enough? And then we could also switch at S1 and then is the green and the blue too similar? Can people see it enough? It is too similar? Alright, yeah, alright. Let me use a different color. Alright. Red just always seems so harsh, but I guess that's a good thing here. Alright. Okay. Alright. Alright. Okay, so let me redraw this with red. Is that better? People see that better? Okay, good.
So Ziva, you're actually labeling, you're coloring things, you're not switching colors at cusps.
I'm not. Oh, yeah, I'm sort of. Yeah, I sort of combined
I mean,
the
how's
two
it-
paths. That's, you're right, that's different than what I said.
How
You're
does it go
right.
together? Maybe it's better to actually not switch colors at the cusps because it's important that they sort of line up at the two ends.
Yeah, you're right. I actually just combined two different ways of thinking about it. Yeah, alright.
So if they're
Yeah.
paired at the, so I mean, those
Yeah, I
normally
can-
pairs
yeah.
these things together, and if they're paired at the left, they need to be.
Right, you sort of have paths that are paired together, and I was doing the two paths paired together with the same color, which I realize is now really confusing. Sorry. So yeah, so it's disjoint. Let's say pairs, but then they're not disjoint. Okay. I don't know if I can. All right.
Maybe just say pairs of paths, and
Pairs of paths.
everyone can think of somewhat district.
Somewhat, yeah. So sorry. Yeah, that was really not.
So basically, just
Except that.
Except the crossings, yeah.
Yeah, except that. Yeah. Sorry. Yeah.
so basically you have to go from one cusp at the left to one cusp at the right, and then go back.
Yeah. You have two paths for each pair of
So
cusps
it's a pairing.
that you. Yeah.
A pairing
Sorry.
between left cups and right cups.
And they
Yeah.
can't cross that anywhere in the middle.
Cross or switch.
No, I mean, the
can't cross
paired
each
things
other.
can never come together at a crossing.
Yeah. Right. Yeah. Yeah. I didn't even realize I was doing that. Yeah. Okay. But now does that? I can. Yeah. Okay. Yeesh.
That's not automatic.
Yeah, I mean, in this picture.
Is this the reason that S1, S2 is not ruling?
In this example.
It's not normal.
Oh, that's one that's not a ruling,
yes,
that's
it's not.
correct, yeah.
So this is the not normal one.
It's part of the definition.
Yeah.
Yeah, everyone's thinking that this.
What do you mean by pairs of paths?
So you, all right, yeah, maybe this is why I should have actually given a real definition. You sort of pair up the cusps, and for each cusp you get two paths between the cusps, and then you can pair them together. So each path is disjoint in this way, but when you pair them together, they're disjoint in the other way.
Maybe you should change your cusp picture to be all the same color.
Yeah.
Yeah, I scribbled, but
She tried to
I'll
draw over it.
erase and do that. Sorry guys, yeah. Right, sorry, okay. I made that way more confusing than it had to be. Okay. But at least, like, okay, but the example's correct, so we can see sort of the two pairs that are now not disjoint at cusps, and how they pair together, and you can either switch or not switch at crossings.
Are you
Yeah.
going to tell us why that one in the middle is not good?
Yeah, you sort of see that this is sort of underneath this too much. There's sort of, yeah. Yeah.
Too much in the.
Well, here, just draw the lines around that crossing.
Like this sort of thing.
On
Or you
others-
mean-
The two on,
Just to the left or just to the right of the crossing?
yeah, just
Either way.
one big vertical line just to the left of that crossing and one big vertical line just to the right of it. Yeah, like all the way
All the
down
way
the
down.
diagram, yeah.
Right. It has to do with the ordering of these points. Here you see this is between these two, and that's not good. Okay, sorry that got more confusing than it should be. Okay, right, so, but we see at least that it's some combinatorial tool that decomposes our front diagram in a certain way. Right. Okay, so, right, was it, I think it was Laura who asked, like, how do you, from a front diagram, can you see, maybe it wasn't, can you see a generating family? So the answer is from a front diagram with a ruling, you can create a generating family. With a normal ruling, sorry. Right, so we want to construct, you can go both ways, but in this talk we're going to go this way. We want to construct a generating family from, you know, the combinatorial data of, I guess, a graded normal ruling. I haven't really talked about any sort of gradings or anything yet, but you sort of want, like, if you have a cusp, you want, and this has a grading I, sort of a relative grading. You want it to go I plus 1 when you go up on a cusp, or not up as in a, like up as in the Z direction. Right, and if you have a switch, you want them to be of the same grading. That's all I'm really gonna say about that. Right, so we're gonna create a Morse complex from this data of a graded normal ruling.
The
Right,
gradings
so,
are on the strands.
huh?
The gradings are on the strands.
Are on the strands, yeah, exactly, yeah.
Is that the index? Of the critical index point?
Yeah, up to a shift of everything, yeah. Mhm. Because I want to go. I sort of want to separate my crossings for this. Kind of want to separate everything in t-values. Okay, yeah, so let's say, I mean, I'm just gonna give a recipe, so what the actual ruling is, sort of pick your favorite one that's not this one. Right. So let me give a. Okay, so, right, so, because we want it to be a linear, I guess I didn't say that, but. Because we want it to be a linear at infinity generating family, we're gonna pick a nice linear function. The big N we're gonna get from the grading, but it's not that important how. But so from the grading, you know, we can pick N so that all of the numbers are sort of in between, like 0 and n plus 1. So we're going to construct the FTs. So. The grading gives you what that N is going to be. Again, it's up to shifts, but yeah. Right, so. So outside of this front diagram, we're just going to have any nice linear function we want, so. So this gives us linear at infinity. Well, mostly, but yeah. Right. So then, as we move forward in t, when we hit a left cusp. So what we're really creating is, I guess we're constructing. A Morse complex, and then the idea is that we're gonna construct a Morse complex, and then we're gonna pick our functions to be as nice as possible to get that Morse complex. I'm not gonna actually write down any functions really, but.
Sorry, n is equal to what, right?
Here, no. I'm not doing it for this example specifically. This is just sort of a picture, but you would need 2, because if you went like 0, then this would be 1, these would be 1, and then these would be 2.
No, but the big capital N?
Big, yeah. Yeah, it's not 1. Okay.
Did you have to like somehow prove it to separate the critical points?
Yeah.
How?
It's nice to do that, yeah. Because,
never mind, okay.
yeah, because everything's up to, you know, Legendre and isotopy and, or the invariants are at least, and up to, fiber preserving diffeomorphisms. We have a lot of sort of wiggle room here. Yeah.
So I don't know if that was the confusion, but the axis that goes from minus k to k is the t direction.
Yeah. Right. So sort of as in the Anat example, the cusps have to do with births or deaths of critical pairs of critical points. When we see a crossing that is not a switch, so a non-switch crossing, what that amounts to is sort of is so right. We're also separating our critical values, except for at crossings when we see a critical value sort of coinciding and then switching which one's a larger critical value, but not that sort of switching. Sorry. Yeah. And then the switches correspond to handle slides. Which is why you see we need like switches to have the same grading. So there's more details in the paper about exactly what sort of handle slides. There's some pretty nice pictures too. But that's all I'm really gonna say about that. It's just sort of like an idea of the ingredients. And then now that you know the ingredients, you can do some bifurcation analysis to understand the generating family homology. Good. So in the last 5 minutes, I just sort of want to mumble a little bit about some newer approaches relating augmentations to generating families.
Maybe it also makes sense to say that from generating family you can also get exact Lagrangian theorem. It's not necessarily embedded. You know that you can also do this kind of decomposition family.
Mhm.
What's functional interpretation.
That's true.
Sorry, can you
Yeah.
elaborate on this for a second?
Yeah, what I'm saying is that from whatever generating family you always get exact Lagrangian theorem. It's not necessarily embedded.
But it is exact. Yeah.
But it's exact, and you can get it more or less from the kind of decompositions.
Yeah.
What's functional.
Yeah, and so there's also a generating family idea for Lagrangians, and the generating family of the Lagrangian relates to the generating family of the Legendrian. So
Can you maybe
it's
spend 5 minutes after the lecture speaking about this?
yeah.
Okay, great. Thank you.
Or you can delegate Roman to explain.
Yeah,
Yeah, maybe we could team up. Yeah, because I don't work with that much, so I don't know if I know the definition off the top of my head, but I can help.
Maybe
Yeah.
it's worth pointing out that this really uses linear and infinity.
Yes.
Sure. Yeah.
Because, I mean, there's a lot of other types of generating families, and if you don't control what's happening in infinity, you won't be able to observe it.
Yeah, that's a very important feature. Yeah, that is very true.
And can you compute generating homology, generating family homology from the ruling combinatorial?
I mean, if in the sense that like you have a Morse complex and the way you would compute the homology of a Morse complex. Yeah.
I think not because there's many generating families can correspond to one ruling, so I think the generating family homology of these different generating families contain fine information in the ruling. The rulings are kind of weak, very weak. I think you can get much about the complex even.
But ruling with some degradation, you can
That's true.
Okay. Yeah. Right, yeah, so, so you can, I'll say, we can try, to relate generating families, to augmentations through sheaves. So, we'll hear more today about augmentations and sheaves. We already heard some. So from, right, so I talked to Vivek while he was here, and from a generating family you get a sheaf. But it doesn't always go the other way over all coefficients. So I won't claim to be an expert on that at all, but I guess Vivek's not here anymore, but I would say bug him about that.
He's still around.
Oh, great. Okay, good. All right. We'll bug him, not me. Right, so I guess I'll just say, like, you can go generating family to sheaf, but you can't always go, and maybe this is in the not case. So.
Or obviously it's not currently known. I think, okay, there are some obvious
Right,
instructions,
there's some.
but the interesting result, we still don't know whether it's true or not somehow. Whether
Yeah.
they're still working on it, I think, but they still don't know. Maybe we can't prove.
Yeah.
I think they claim they know how to prove it.
Yeah.
Not me too.
Last week I didn't.
Okay. Yeah, I couldn't get a very clear answer. Yeah. 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 My main question was, I don't know if I should say this is open or not, so I don't know. All right. And then I guess, I don't know, Pan wanted me to say that there, is more, so there's all this algebraic structure for augmentations. I guess we haven't quite talked about the augmentation category yet, but you might wonder, like, what about algebraic structures, like, of collections of generating families? And so Pam wanted me to say that one of my current, what I'm currently working on is sort of a infinity category of generating families using moduli spaces of Morse flow trees. So if you're interested, I can tell you more about that if you want to know. Okay. In progress though. Okay, and I'll stop there.
Any questions for Zena?
Do you know if anybody will talk about this splash construction, or it's not? Can you say anything?
Yeah, I thought, is someone talking about it?
Who's doing augmentation?
Yeah, I'm going to use it because you have a perturbation scheme which uses splash construction, but that's not the key point in my talk.
You want it to be? No, I'm just kidding. I mean, I can't say much about it, but I can say the little I understand from this paper. Right, so you take a Lagrangian projection and you sort of decompose it. Is this the right way? Yeah. I don't know. I'm not going to do this on the fly exactly how to do it. I'll maybe just wave my hands about it. Okay. You decompose it, you sort of slice it up so that you only have interesting things like crossings and cusps in each slice. And then you sort of do, which way do you go? You go,
So the front projection easier, isn't it just pinching something like that?
yeah, dips go down, splashes go up, dips go down and over, splashes go up and under. Okay.
And the splashes are separated, they're like one at a time, the dips are kind of all at once.
Splashes are bad. You should never use splashes.
So never use splashes, but the paper I
I
read.
tried to convince Stan of this at some point and I failed, but. Yeah.
You failed?
He's now using dips, right at the moment.
Okay.
You may not be happy about it, but he is.
Is this the audience participation part? I can draw a picture.
Sure, you'll be better at this than me, for sure.
Then we can call it Roman too, it's fine.
Oh,
Don't want to erase anything.
you can erase anything.
So here's the front projection and the Lagrangian projection. So you have some sort of. No, I actually don't want to draw too much of this. Okay, so the idea is that up in the front diagram we have some maybe collection of line segments, and then what we want to do is we want to localize the XY picture so that all the holomorphic disks become localized. And so the idea is that we split this diagram into interesting pieces, which each piece only has one crossing or maybe one of these things or the things on the other side. And then between these things, so right in the neighborhood of where I'm splitting it up here, the front projection looks something like this. So that the slopes are slightly different, so that the slopes are the y coordinates. And we replace this by, let's see if I can draw this. Something like that. And what that does is that downstairs that replaces this by something like this.
Lagrangian projection?
Yeah, so this is front projection, Lagrangian projection, yeah. And this has, I mean, this is sort of like in Morse theory, or you break up the flow trees into pieces so that none of the Morse flows can actually go past all the way through this region. Everything's sort of forced to die inside of there. So this has the effect of making the differential a lot in LCH a lot easier at the expense of having many more rich bits. Thought I had something else to say, but I think that was it.
So geometrically, are you taking this cobordism, the inverse cobordism, and then you getting the augmentation that you get out of that cobordism?
This is an isotopy.
This is what, I mean, you can decompose, the upshot is that you can decompose your DGA as some push-up or some smaller pieces. So everything becomes local now. And that's maybe it's easier to...
In this one-dimensional case. That's
yeah,
right.
right. And then
there's some similar picture in 2 dimensions, which is more complicated.
But it hints like the connection to sheets as well. Because now
correct.
The DGA is decomposed in this manner, so it's local.
But as you come at it, you have a generating family, you can commute that away, and then you get some Lagrangian cap, and okay, it's immersed, so maybe not, but you can't hold holomorphic curve there.
Well, maybe this is a good time to... Yeah.
Yeah, maybe before
I
that.
can give you a reference.
No,
The
no,
precise
you have to
reference.
stand up.
Well, I really need to prepare a bit in order to stand there, but I can really give you a reference to the precise construction.
Of the cobordism. I can do that.
You can do that?
Oh, Thomas can do it.
Okay.
Oh wait, so Marco,
Wait,
you had
yeah, I
as
have a
he's
question.
coming up, you had a
Why was
question.
everybody cringing for the notation? Somebody was complaining the notation.
Usually, like the front projection is like XZ, and this way was T, and then X was the fiber coordinate.
Oh,
and like,
So
It's
so
just a
there should be a
permutation of
global
that.
search and replace. So L should be
yeah,
lifted.
that too.
L
What was capital L?
Capital L should be.
Capital L should just be like
Capital
the
L should
front.
be the front projection.
Yeah. Yeah.
Yeah.
And then like T should be X and X should be, well, E, I think.
E,
But
yeah.
It's just a
yeah.
limitation of letters.
It's just, yeah, it's just a, it's just, yeah.
Okay.
So a generating family linear
Yeah,
at
not should
infinity.
switch. But no, that's the right way.
Yeah. So this is a generating family of sumless Gendring in jet 1 of R, which has some sort of critical points here in the RK factor when you fix some point T, and the bifurcation of that is giving you the front projection. So the bifurcation diagram of the critical points is the front projection. Now if it is linear at infinity, you can just write down R2 cross RK, let's maybe call this small f. Now ft is just going to be f depends on t, an extra coordinate here, and it's just the old f plus whatever linear function you had at infinity. So just interpolates, so it creates a new, maybe I should put I, cross I, and this I is the t. So you just sort of take convex interpolation between what function you had as a generating family to the linear function. And maybe I should start with t 1 minus t times f plus t times linear function.
Can you call T something else?
S.
Okay. S. So this just convexly interpolate in this new S factor between the the function that generated to the linear function at infinity. And since they look similar at infinity, it's only going to have something on compact sets. But at one end, over S equal 1, it's the empty set that it generates because it's a linear function. But over the other end, it generates what we saw. Of course, you have to perturb it a little bit to make this generic, but then you get a generating.
So this gives you some exact immersed Lagrangian and
Yeah, with the
an
generating
augmentation,
family
and it
as
has
well.
to be the same augmentation.
Wait, but
Don't you have to like pass through the symplectization?
it gives you, it's giving you a Lagrangian, and then you're taking a Lagrangian.
Yeah, you take the Lagrangian projection,
You
so
have to
it's
pass
immersed.
through a
But there's a
symplectization.
Lagrangian on the boundary.
Yeah, just.
This is
If you want to see the construction details, it's a proposition 3.1 in sublog bourgeois and Trainer. I think the name of the paper is Lagrangian cobordism sphere in generating families.
I think the author is uniquely determined.
Okay.
Yeah.
I mean, I think maybe there was a comment saying that I'm generating something in jet 1 of R cross I.
That's right.
And you can Lagrangian project to a Lagrangian immersed cobordism in T star R cross I.
You can always resolve the Lagrangian, right?
But then you lose exactness.
Yeah,
So the,
yeah,
as it is, it's an exact immersed, which is not as bad as it sounds because it's unobstructed.
yeah.
Mm-hmm.
It's unobstructed, but I mean, you can think of that as being, because it has a generating family,
Yeah.
that gives you a sheaf, or that's an augmentation, which is a bounding cochain or unobstruction cochain, or it's all the same thing maybe.
And also from the point of view of bourgeois, sublog and Trainer, it's nice, this type of feeling, it's nice because it actually supports the generating family, you can extend it through.
Mm.
Because it's useful if you try to play with, in general, cobordisms, you will like stack them and to do some sort of like a TQFT. So from this perspective, this exact Lagrangian feeling is nice.
Vivek, come here. What's the status of your work with Sylvan?
So, what's the question? I think the short summary is that in one dimension, like when you have generating families over one-dimensional base, then sheaves over. Now I would say, like, if you try and extend from left to right, the lifting of a sheaf to a generating family, it works if your sheaf is a sheaf of spectra. So in dimension 1, sheaf of spectra is the same as generating family. But it is not true that you can lift. You can ask like 3 levels of this question. You can ask, what happens if you try and lift a sheaf with like Z2 coefficients to Z coefficients, sheaf with Z coefficients to spectra, sheaf with spectra to generating family. And the final stage is an equivalence, lifting from Z to spectra to obstructions. No, that's not true. We don't know what the obstructions. We don't know if the obstructions to lifting, but we know that it's not unique to lifting. And lifting from Z2 to anything is possible, but again, uniqueness is. But in higher dimensions, we're currently of the following opinion that, for example, the 2-dimensional unknot admits 2 inequivalent generating families, but only 1 sheaf of any kind. So it seems like some sort of guess is that maybe if you keep the sheaf of spectra plus the Gauss map, that's something that the sheaf of spectra definitely forgets the Gauss map. Maybe that's the.
And the Gauss map is how you tell apart these 2 inequivalence things.
The Gauss map doesn't quite. It's something related to the Gauss map.
So is it correct to interpret it like if you really consider generating families to sheaves, that there is a math function related to families to sheaves?
Yeah,
It's surjective, but not necessarily objective.
I mean, it's surjective, need not be injective, and it need not respect. I mean, they have different generating families of the same
Yes.
sheaf. However, generating.
That's
not necessarily.
Not
surjective.
necessarily.
And
and not necessarily injected.
Yeah.
But what is true is that generating family, any known invariant that anyone has ever made out of a generating family, factors through sheaf. That's
It's like a universal.
no, we just don't know how to extract. There's other information in generating families we don't know how to extract.
I see.
Is that true? Like pseudo-isotopic invariant?
No, not these ones. But some
Okay, so not.
Yeah.
Well, I mean, how do you use that to distinguish the genre?
You can find knotted things. Knotted.
Anyway, short answer is no. I mean, that's precisely the stuff that gets killed. And we don't know how to get it back.
It's too related to uniqueness. We could have another generating family with another pseudo-isotopic at the moment, so.
Okay, Pan, you're in charge. You have to.
Alright, so the Talking Afternoon Story 2. Alright, so Steve?